Today we're going to talk about ideal chain statistics. And so what that is a set of assumptions, or the result of a set of assumptions, and what it tells you is something about the entropy of a polymer chain under ideal conditions, and the size and the shape of the polymer chain under these ideal conditions. And eventually these sorts of things, the entropy, for example, are used later on down the road when we talk about things such as the size of a polymer chain and what that has to do with the mechanical properties of materials, the mechanical properties of rubbery networks, so think rubber bands and things like that, and certain related things. So the most important thing that I want to get to is that what we're really talking about here is entropy. Okay, and so what we came up with recently was an expression for the entropy of something. And notice that this entropy that I've written, this is not equal to delta S. And so one of the things that we've been focusing on is calculating changes in the entropy of a system when it goes from one state to another. So for example, if a polymer chain was to undergo an isothermal expansion, then there would be a certain change in entropy associated with that process happening. But what we're going to be talking about today and in the next few videos is this absolute value of entropy. So what is the entropy of the system? Not the change in entropy, but what is the exact entropy of the system in terms of a certain number of joules per Kelvin or something like that? So that's where I want to start. And this equation in particular that I've written down behind me, this is a special case of entropy. This is what we refer to as the Boltzmann entropy. And it applies in certain conditions, but it doesn't apply under all conditions. It's going to apply to what we're going to be talking about in terms of a polymer chain. In fact, it's very good for the case of a polymer chain, but it's not going to apply in general. So just to give you a little bit of information about entropy, and remember when we talk about entropy, although it's traditionally or very typically used as a measure of disorder, it is not describing the disorder of a system. It's talking more about how much you know about a system. Okay, so if you know very little about a system, if you have a large number of microstates that a system could have, if, for example, all you knew is that the energy of your system had a certain value, there could be an enormous number of microstates, the certain arrangements of the particles in your system that would give rise to that entropy. And so generally high entropy systems are systems where you don't know a lot about them because there's so many different microstates. So regarding entropy, high entropy is associated with knowing very little about your system. Another way of saying that is if you know very little about your system, then that must mean that there's a large number of microstates. There's a large number of possible configurations that are possible for that system. So this goes along with saying that there's a large number of microstates associated with that. So in the most general sense, if you wanted to talk about the entropy of a system, the way we define it is something like this. And the letter that we use for entropy tends to change, but let's just call it S so that we can stay consistent with what we're talking about. And so the entropy is most generally calculated as the negative of some summation of the probability of something happening. So the probability of a particle being in a certain energy level, the probability of a particle having a certain position in your system, multiplied by the logarithm of some base, b, of that probability. Okay, so this is the most general thing. And what you're summing up here is x's that are possible. And so the way we typically define this, there's going to be a certain probability right here of x occurring, okay? So for example, there's going to be a certain probability of a monomer having a certain position, and we're going to add that up. Well, first of all, we're going to multiply that by the logarithm of that probability, and we're going to add that up, in this case, for all x's that are possible. So what I've just written down here is what we call the Shannon entropy. And it's the most general entropy that we could talk about. We're not going to use it because the one thing, if you notice here, is that this definition depends on the probability of X existing. Okay, so there could be different probabilities. It could be more likely than not that a monomer would be over here than it would be over here. Okay, in that case, these probabilities are not going to be equal. But what we're going to do is restrict ourselves to the cases where we don't need these probabilities. And I'll get back to that in a second. But Shannon entropy is useful if you're a polymer scientist. It can be useful, for example, in processing images. So for example, Professor Manas in our department worries about, or studies, I should say, distribution of nanoparticles in polymer materials. So she's interested in the distribution of nanoparticles in what we call a polymer nanocomposite. So how do you quantify how dispersed something is, how spread out the nanoparticles are? One way that you can do that is by calculating a Shannon entropy. And in this case, a large Shannon entropy would correspond to well-dispersed particles. Okay, so for example, in this case of processing images, X could be a pixel in your image, and I'm talking about something like a JPEG, PNG, etc. X could be a pixel, and X could take on a value of 0 if it was black. Okay, so that might be a place where you're imaging the nanoparticle. Or it could be 1 if it's white. In other words, the background of the image. So imagine you're seeing these like black spots on white. And then you could figure out what is the probability of that certain pixel having a value of 0 or 1, and you could sum it up. In fact, since there's only 2 values possible for this example I'm giving you, it might make sense to define the entropy as minus the summation over X, in this case could be all the pixels, multiplied by the probability of that pixel being 0 or 1, multiplied by the log base 2 of the probability of that pixel having a 0 or a 1. Okay, so this thing right here is going to give us what we call bits, which are the same bits that you talk about in terms of computer storage, right? There's a certain number of bits that your computer hard drive or solid state drive can store, and it's the result of individual transistors in your computer's hardware being able to take on a value of 0 or 1, not unlike the case of the Shannon entropy. Okay, so Shannon entropy is something that computer scientists will use a lot. It's also very useful for image processing. It's useful for a bunch of things. You can get some special cases of this. One special case is that you can calculate entropy similar to the Shannon entropy, but with this constant in front. So you can calculate it this way. This is what we call the Gibbs entropy. And all it is really is the Shannon entropy, but it has this coefficient out front, which is really just a conversion factor. All it's doing is giving entropy specific units, in this case, joules per Kelvin. Okay, so the Shannon entropy has no units. The Gibbs entropy does have units, and they're given by that constant. One common thing that we would do here for the Gibbs entropy is we would take the log base E of that probability, which would give us an expression that looks a little bit maybe more familiar. We would have log P of X. Okay, so that's a special case of the Shannon entropy. Another case of the Shannon entropy can be used for quantum systems. Okay, so for quantum mechanics. We're not going to talk about that this semester. We don't talk about quantum mechanics in this class. But just so that you know, this is called the von Neumann entropy, after John von Neumann. And then finally, we can have another special case of this entropy, where we get something that looks like entropy is KB log of omega. And this is what we call the Boltzmann entropy. Okay, so the Boltzmann entropy is similar to the Gibbs entropy. The only difference is that you'll notice that there's no probability out front, and that we're looking at the number of microstates as opposed to the probability of something being in a certain position or microstate. Okay, so we're assuming that all the probabilities are the same. The minus sign goes away for mathematical reasons, and we get the KB out front still, which is just a conversion factor to give us the proper units. And so this is the only thing that we're going to focus on in this class. And as you'll see, this allows us to calculate a bunch of different properties of polymer chains and give us some insight into why the materials behave the way that they do. Okay, so remember, by using this formula, what we're assuming is that every microstate is equally probable. Now let's go back and try to make some connection between this discussion right here of entropy and a way to calculate the absolute entropy of something and the 1D random walk that we were discussing very recently in class, okay? So the 1D random walk we looked at in terms of the number of possible ways that we can get to a position X. So the number of possible ways, the number of different ways that we can get to a position X in this alleyway that I'll draw in a second, is the number of microstates. And so this problem looked something like this. We had an alleyway, and someone starts in the middle of the alleyway initially. And what they do is they take a certain number of steps. And so the number of steps that they take in this direction, we call capital N. And they move a certain distance in this direction that's the same every time. So for every step, they're moving this way a certain distance. But remember, they were unsteady. And so for every step, they could move up or down a certain amount. So let's say that after one step, they could move up here +1, or they could move down here a distance -1. So the only rule was that they had to always take a step forward and always take a step in the X direction. So simultaneously, they're taking a step and they're kind of stumbling to one way or the other. The size of that stumble in that direction is always going to be the same. And as to whether they go left or right, that is random. So you can see that after 2 steps, there is a chance that the person could go back to the center of the alleyway, or they could move up to +2. And in terms of the other possible walk, let me give it a different color. They would also have the probability of going back to the center, or they could go down here to -2. And then you could see what would happen with the next step that they take. Let me choose yet another color. They could move from this position down here to +1. They could move up here to +3. If they were down in the center of the alleyway, they could move up here to +1, or they could move down here to -1, or they could move, let's see, any number of different ways, right? They could move up here, down here. So you see, it starts to get really complicated, the number of different ways that they can get to different positions in the X direction. So instead of looking at this complicated example or this complicated picture of the alleyway, let me draw it a different way and see if that helps a little bit. So in this way, let's imagine that this alleyway, all we really care about, if you think about it, is how much the person walking down the alley has veered up or down. That is, what is their position at the end of the day? So if you think about it, because we don't care about how far they're moving in this direction, that's not something that we're concerned with, then this really is just a one-dimensional random walk. We're looking at how they're moving up or down in the alleyway, maybe kind of like this, right? So I could draw on the x-axis their position. So almost just like on a number line, here is x. We're looking at what their position is in the alleyway. And so initially, the person starts at x = 0. So this is their position. And next to it, let me draw a graph of the probability of them having that position in n steps. Okay, so on the x-axis will still be their position, and I'm going to plot on the y-axis where they actually are in terms of the probability that they're at a certain position. Okay, so what that would look like is initially, if this is x equals 0, initially there's a 100% chance that they're at x equals 0. Do you see why that is? Because initially, that's where they are. That's where they've come out the door into the alleyway, if you want. And then let me also say that this x equals 0, this is after n equals 0 steps. But then what happens? Well, then the person takes a step, and they can either move up 1, kind of like that, or they can move down 1, like that. So after 1 step, there's a 50% probability that the person could be at a position of +1 in the x direction. And there's a 50% probability that the person could be at -1 in the x direction. And there's a 0% chance that they're exactly in the alleyway, right? And you can see that, let me change colors. You can see that right here. There's no chance that they can be there. All right? So that means that after 1 step, there would be a 50% chance the person could be at +1, and a 50% chance that they could be at -1. And then they take another step. And so from this position, there's a certain chance that they could move back to 0, so they could take a step in the negative direction, or they could take a step in the positive direction to go to +2. And that's what we're showing right there. And if the person was already at -1, then there's a certain chance that they could take a step back to the center of the alley, or they could take a step in the negative direction and be at a distance of -2. Okay, so they're randomly moving back and forth just because they can. There's a 50% chance that they take a step in the positive direction and a 50% chance that they step in the negative direction. So after, let me annotate this figure a little bit. This is for 0 steps. And this is for n equals 1 step. Now what happens after they take 2 steps? Well, I'm going to change colors to try to keep this readable. There's 4 possible positions that they can end up at, right? After 2 steps, 2 ways lead to the middle, and only 1 way ends at ±2. So there's a 50% chance. There's 2 ways out of 4 that they could be in the middle of the alleyway. There's 0 chance that they could be at a distance of ±1. And out here, there's a 25% chance that after n equals 2 steps, okay, so this point, that point, and now this point is after n equals 2 steps. Okay, so you see the probability, as you're taking more and more steps, this probability distribution is changing a little bit. Okay, so let's draw this again. If we think about the number of different ways that we can get to the points, this is what I showed last time. If we plot on this axis the number of steps that we've taken, and then on this axis we plot where that person ends up, then we get the following. For n equals 0 steps, there's 1 way that they can, there's 1 place that they can be, right? There's only 1 place they can be, and that's x equals 0. After x equals 1 step, after n equals 1 step, the person could be at -1 or +1, and there's 1 way to get there and 1 way to get there. Of course, in the previous step, there's 1 way for the person to be at x equals 0. Okay, so this is, again, n equals 0. These 2 points are for n equals 1. Then after n equals 2 steps, there's 2 ways that they could end up in the middle. There's 0 ways that they could end up at ±1, and there's 1 way that they could be at +2, and one way that they could be at -2. Okay, and this goes on and on. So eventually you'd see you get 1, 3, 3, 1 for these different positions. This would be, let's see, this would be n equals 2. This would be n equals 3. And we can go on and on and on. And what you noticed in class is that this looks a lot like Pascal's triangle. Okay, so this is similar to Pascal's triangle. In other words, Pascal's triangle is telling us for each n, let me write it one more time. This is n equals 0, n equals 1, n equals 2, and n equals 3. For each value of n, we find that the number of different ways that we can get to a certain position is given by the coefficients from Pascal's triangle, which you remember, or I hope you remember, is related to the coefficients of the binomial expansion. All right. Okay, so what we've identified so far in doing this is that if 1, there's equal probability of taking a step in the plus x direction as there is for the minus x direction. Okay, so that was kind of our assumption. If that's true, then that means that the number of microstates for each position x after n steps is related to the coefficients from the binomial expansion. Okay, so that's one reason that they make you do this when you take algebra, right? This is useful. It comes up in a number of different places throughout science. And so what we did in class is we kind of assigned this. We said that the ways that there are to get to a position x in n steps is actually the same as the microstates. Okay, in other words, what is being held constant? If you want to make an analogy to the energy example that we did with the different energy levels, what is being held constant here is the position that we're ending at after n steps. So the number of ways that there are to get to that constant position in n steps is the same as the microstates. It's the number of different rearrangements of steps that give us the same result, that give us that position x. Okay, so again, this is, if you want to put words to this, this is the number of independent ways to get to position x after n steps. So, if you think about it, what is this? Well, again, if we're making the connection between this thing, the number of microstates that exist for a position x after n steps, we're making a connection between this and the coefficients of the binomial expansion. And these, if you remember, these are the combinations. Okay, so this is telling us something else. This is telling us that the number of microstates for position x after n steps is the same thing as the number of combinations of capital N. Maybe I should use different notation so we don't mix these up. Let's call this, see, what do we want to call this? Okay, so the number of microstates corresponding to position x after n steps is the same as the coefficients for the binomial expansion. And this is the combinations of m elements taken k at a time. So this is the same thing if you're looking at your calculator of kc m. Okay, it's the number of combinations. Notice that this is different than what we did with the energy levels. The energy levels, we were looking at permutations, okay? That's because that was a very specific system that had certain properties. For this system, where we're looking at the random walk, I hope you can see by analogy between Pascal's triangle and counting the number of ways that that has to be the number of combinations. Okay, so the definition of that, if we were to look in our algebra textbook, would be m factorial divided by k factorial m minus k factorial. Okay, so again, this is number of combinations. All right, so what we can do is if we want to make this connection, then this number of microstates, if we want to use the same terminology, the same symbols that we've been using here, the number of microstates that exist for position x after n steps is going to be the total number of steps. So total steps factorial divided by the number of steps up factorial, so that's the number of steps, let's say, in the positive direction, and the number of steps down factorial, that is in the negative direction, okay? And hopefully you can see the connection between something like this and m factorial steps up as k factorial. And so if you're taking m total steps and you've taken k steps in the up direction, then that means that m minus k factorial should be the number of steps you've taken in the negative direction. All right. So let me just write this in a different form, and then I'm going to directly give you the result, but I want you to see the connection between this and what we've been doing. So let's say you take n plus steps in the positive direction, and n minus steps down. Then the total number of steps that you've taken n is going to be equal to n plus n minus. And the position that you get, let's say that every step that you take in the x direction, every time you move up or down, is going to be the same length, and let's just say that it's equal to 1. Then the position that you are in x, so your position is going to be the difference between the number of steps you took up and the number of steps that you took down, right? That will give you your net position in the x direction. Okay, so all this means is that the number of steps in the positive direction is equal to n plus x divided by 2. And the number of steps in the negative direction will be n minus x over 2. All right. And remember, the magnitude of each step that we're taking is going to be plus or minus 1. And so at the end of the day, the number of microstates that we have for a position x after n steps will be n factorial divided by n plus x divided by 2 factorial, n minus x divided by 2 factorial. And now what's the total number of independent steps that we can take? So ignoring position, if I take n total steps, so if I take n total steps, how many different ways can I do that? How many possible unique walks are there? Unique trajectories, unique combinations of moving up or moving down? How many unique ways exist after I've taken a total of capital N steps? Well, what do I say? The value of that, if you want to think about it, when you take your first step, you've got two ways to do it, right? You can move up or down. And then once you've done that, for your next step, you've got two ways to take that step, up or down. And then for your next step, there's two ways that you can do that, up or down, and so on and so forth. Until your last step, you can move up or down. And so if you take a total number of these, if you take a capital N number of steps, then the total unique, so the total number of unique paths is just going to be 2 to the n. Okay, so remember, the microstates that we've calculated, this omega of x and n is, if you're at a position x and you've taken n steps, how many unique ways are there for you to get to that specific position x after n steps? This thing I've calculated down here is different. What it's saying is that if I take n steps period, then there's 2 to the n ways of uniquely doing it. Okay, so this microstate, this number of microstates depends on the position. It's how many unique ways can you get to this certain position after n steps. This thing down here is how many unique ways can you take n steps, regardless of the position that you end up at. And so that's where we get that the probability in one dimension of ending up at a position x after n steps is going to be the microstates, the number of microstates for that position, divided by the total number of ways that you can do it. We've calculated the total number of unique walks that we could have, which again doesn't depend on position. So this is equal to the integral of omega of x and n dx. In other words, we integrate the number of microstates for all of the different positions we could end up at. That's the same thing as the total number of unique walks. And that gives us omega of x and n divided by 2 to the n. So this is important. This is something that we're going to come back to so that we can start to calculate the properties of polymer chains. But in the meantime, the important thing is that if n is very, very large, so if n is much, much, much bigger than 1, then this expression simplifies, okay? Because this thing in the numerator, remember, this is related to more or less n sub x, right? So it's related to those binomial coefficients. This thing in the denominator is what it is, okay? It's just 2 to the n. If n is much, much bigger than 1, this thing simplifies so that the probability of ending up at position x after n steps is something like this. Square root of 2 divided by pi times capital N, all of that stuff in the square root. The exponential of minus x squared over 2n. Okay, so there's a lot of math here. To get from that step to this step, there's lots of math. And while it's important to be able to do that, it's not really that important for the purpose of this class. So the second thing I would say is that this expression is going to be very important for us. This is the probability distribution for a 1D if n is very, very, very large. And so I can schematically tell you what this corresponds to. Let's say that I've got something like this. So x is equal to 0 in the middle. If I have 0 steps and I get this spike, I get almost this delta function in the middle. And there's a 100% chance that after 0 steps, you're in the middle of the alleyway. Then I take some steps where n is greater than 0. And n is big, but n is still greater than 0. Then my probability distribution will start to evolve a little bit. And I'll get something that looks like this. And so on the x-axis, is still the position. On the y-axis is the probability of being at that position after n steps. Okay. And so it's still centered about x equals 0, but now this point right here, it's now less than 100%. So you start to develop some finite chance of being away from the origin, but you can see that the most probable position is still at the origin after that many steps. And then you could do this even more. You could take a much larger number of steps. Okay, so x and n prime, let's say, and look at the probability that you'll be at a certain position. So let's say that this is x equals 0, and let's say that this number of steps is much, much bigger than the ones that we took above. Okay, so in other words, we've taken more steps. What does our probability distribution look like? It starts to get smaller, so it squashes down in terms of its magnitude, and then it spreads out to the side. So the probability of you being farther away from the origin increases. Your probability of being at the origin is still the highest percent, so this is less than 100%. But you can see that in these regions out here, you start to develop a non-zero probability of being out there. But at the end of the day, your most likely position is x equals 0. Okay, so talking about the person in the alleyway, this person right here, if I was betting money on where they're most likely to be after a certain number of steps, most likely they're near x equals 0. At least according to the statistics, according to the probabilities that we've calculated. Now, is there a chance that they could be way out here? Of course, right? There's a finite non-zero probability that they can be out there. But if I was looking at the most probable place that they would be in the middle of the alleyway. Okay, so that's in one dimension. If I wanted to look at this in 2 dimensions, the probability in 2 dimensions of having a position x and y after n steps, you could assume that the probability of moving in the x direction is independent of the probability of moving in the y direction. So this would look something like some coefficient out front times the probability distribution of x in 1 dimension, the probability of a position y in 1 dimension, and you get the 2D probability like that. Okay? And so in practice, it becomes easier to write this P2D of having a position R after n steps. We could do the same thing with 3 dimensions. And so if we wanted in 3 dimensions, we would get the probability in 3 dimensions of being at a position R away from where we started, so away from the origin, would look something like some 3D coefficient, which just normalizes the probability distribution. And we get P 1 dimension of x, P 1D of y, and P 1D of z. And again, in doing this, the assumption is that x, y, and z are independent of each other. So that may be true or that may not be true. It really just depends on the problem that you're trying to solve. For the case of the polymer chain that we're about to look at, this is always true. And so what we'd like to do now is connect these probabilities. Okay, so for example, 1D or 2D or 3D Gaussian probabilities for random walks. We want to connect that probability for the random walk to the shape of a polymer chain. Okay? So there's a couple things to note here. The first is that, one, we'd like to connect the random walk. And correspondingly, if we connect the random walk to the polymer chain, we're connecting these probability distributions to the polymer chain. So we want to connect the random walk to a polymer chain. And that means that all of the math comes along with us. The second thing is to realize that these probability distributions, so for example, the 3D probability distribution is going to be equal to the number of microstates that we have at that position after n steps, divided by the integral of that thing. Okay, and this is going to allow us to calculate the free energy later on. But the first thing that we want to do, and the only thing that we're going to do in this video, is first we're going to focus on connecting the random walk to the polymer chain. And then in the next video, we'll worry about this. Okay, so first today we'll do this. Second, in the next video, we'll do that. Okay, so what does this have to do with polymers? Well, let's start with a simple polymer and see if we can connect this description of a real polymer to this idea of a random walk that occurs. So the first thing is, let's look at something like polyethylene. Okay, things that make up milk jugs and plastic bags and pipes for natural gas and things like that. It's one of the simplest polymers that I know of, and so let's take a look at it. Here's the chemical structure of polyethylene. And I know a lot of you are at different points. Some of you are sophomores, some of you are juniors, but just if you're not sure or don't remember, this is the number of monomers in the chain in the polymer. Okay, so it's its degree of polymerization. Okay, this is exactly the same thing as if we drew the structure like this, right? We just have a bunch of CH2s connected to each other, and we have N of them. Okay, so in terms of the structure of the molecule, the question that I'd like to ask and then answer for the rest of this video is our first question: what is the size of this molecule? How would we do that? Well, the first thing is, let's take our molecule and let's spread it out. Let's take this chemical structure and kind of expand it a little bit. Okay, so this thing would look like, if I got rid of those parentheses and drew in the structure, my polyethylene would look something like this. Okay, and it would just go on forever. So one of the things that we can do is we could assume that each one of these bonds, so this CH2-CH2 bond, will have a certain length to it, L, and we'll assume that it's the same, okay, that it doesn't vary that much. So that means that each one of these CH2-CH2 bonds here will have a size L. And actually, for carbon-carbon bonds, should say probably sigma bonds. For carbon-carbon bonds, that length, L, is about 1.54 angstroms, or 0.154 nanometers. And actually, it doesn't fluctuate that much. It is pretty much constant. So if you were to look at how much this changes, L is about 1.54 angstroms, plus or minus 0.05 angstroms. So it really is about constant. All right, next thing. Next thing you could notice is that there is a certain bond angle that's preferred. And I've drawn this molecule in a very particular way, right? I've drawn it where all these bond angles are the same. And so there's a certain angle, you can see it here. Or equivalently, we could draw a different bond angle. And we could look at that one. And so that's actually what I want to use. So let's get rid of this theta prime. But you can see that all the bond angles are the same. That angle there is going to be the same as that angle there. And again, what is the goal? What I'm trying to do is figure out what is the size of my molecule. Okay, so I think I have a way to do this at this point. If you look at it, what I can do is I can take that angle and divide it by 2. And I can get 2 right triangles out of it. So if I bisect this angle, then what I'm going to end up with is an angle up here of theta divided by 2, and an angle down there of theta divided by 2. So maybe I can clean up this drawing a little bit. Let's get rid of this. And let's draw one of these right triangles. And you can see that the angle in here will be theta divided by 2, and that the bond length is the same. So that means that for each one of these sections of the polymer chain, there's going to be a length of L cosine of theta over 2 for one side of it, and then for the other triangle, there's going to be L cosine of theta over 2. And you can see that there's exactly one appearance of L cosine theta over 2 for every CH2-CH2 bond, right? So for every one of these bonds. So if I wanted to look at the size of the polymer chain, then the maximum length that I'm getting when I extend this molecule all the way out is the number of monomers that I have multiplied by how long or how much length they contribute to the chain, which is L cosine of theta over 2. Okay, so this is the first really major expression that we have for the size of the polymer chain. And what we call this is its fully extended length. Or you'll typically just hear me call it Rmax. It's the maximum length that you can have for the polymer chain. You pull the polymer chain out all the way until it's completely taut, and that's its length. That's the maximum length you can have. Now, it turns out that for carbon-carbon bonds, this angle is well known. So this theta is about 68 degrees. It's what we call the tetrahedral angle. Okay, so now we've got a measure. So let's do a quick example. Let's do the example for polyethylene. And so our example is, let's say that we have polyethylene with a molecular weight of 150,000 grams per mole. So not a huge polymer, actually. Okay, small compared to things that are used in biomedical applications. And this polymer is polyethylene, right? So that means that each monomer is an ethylene molecule, and we have many of them. So ethylene looks something like this. And so the mass of the monomer is about 28 grams per mole. Okay, so if that's polyethylene that we're looking at, and we've got the monomer that has that molar mass, then it means that the total number of monomers that I have, N, will be 150,000 divided by 28, and that's like 5730 something. Okay, you can calculate the exact value. Okay, so what is R max for this molecule? What is the size of this molecule if we wanted to calculate it? R max would be that value for N. So let me just put in what we'd have. We have 150,000 divided by 28. That's the number of monomers. L, we've got that. So L will be 0.154 nanometers multiplied by the cosine of 68 degrees divided by 2. So if you're using a calculator, make sure you're using degrees and not radians. This will come out to be 684 nanometer. That's pretty big, right? That's a molecule with a fairly low molecular weight that is almost 1 micron in length. I mean, that's pretty huge for the size of a molecule. And the problem is, if we look, we don't see this. So for example, let's say that I put these on a surface. All right, so if this was the shape of the molecule, let's say that I put all of these molecules down on a surface like this, and they're these big, rigid things, and each one of these will have a length of 684 nanometers. And let's say I take an AFM tip. So I do what's called atomic force microscopy, and I drag this tip over the surface so that I can image these things. What I would find is that this thing on the left is not what they look like. In fact, what they look like is something that's much smaller than this. What I would see instead is a bunch of little molecules like that. So much, much, much smaller. And the question is, why is that? So in this case, on the left-hand side, there's no flexibility for the chains. And on the right-hand side, if they're going to instead be these small little molecules instead of these long string-like things, these long rods, then this implies that there must be some flexibility. Okay, so for a lot of polymers, not all of them, but for a lot of them, this means that polymers are flexible. And so for the remainder of this video, I want to talk about, first of all, why are they flexible? What is the mechanism that gives rise to the flexibility? And then 2, what does this mean for calculating the actual size of the polymer chain? And so to do this, let's look at a section of the polymer chain. Let's magnify a section of the polymer chain and see what it looks like. And so what we have is somewhere in the chain, we have carbon atom number I, and it's going to be connected to carbon I plus 1 on one side, right? And because of the way the polymer chain looks, because of, let's say, this structure right here, we know that it also has to be connected on the other side to carbon C I minus 1, which is also going to be connected to C I minus 2, and so on. You could go all the way out to the ends of the chains. And so for each one of these carbons, remember, these are part of the ethylene molecule. So we've got, let's say, two hydrogens that are attached. And so at this point we've got, let me get the right, let's call this hydrogen 1, this hydrogen 2. And over on the other carbon, carbon sub I, we've got down here hydrogen 3 and hydrogen 4. Of course, we've got hydrogens up here. We have hydrogens down there. Okay, so this is what's going to give rise to the flexibility of the polymer chain. So if you wanted to look at this, first of all, these bonds can rotate. So when you take organic chemistry especially, you know that these single bonds can rotate, whereas a double bond can't, or a triple bond can't, right? So there's some rotation allowed for these sigma bonds. The next thing you could do is you could look at a Newman projection of this. So if some of you haven't had organic chemistry yet, you may not have seen this. But if you have, you've certainly seen a Newman projection. And so what we're going to do is we're going to plot, let's see, let me get this right. We're going to plot what is going on this side in terms of the orientation of the bonds with what is going on this side in terms of the bonds. And so the Newman projection for this segment of the polymer chain, the way that I've drawn it so far, will look like this. We've got, let's see here, something that looks like this, and I will label these so you can see what they are. So what we're looking at here, this atom here is carbon I-1. And if you'll notice, coming off of atom carbon I-1 is going to be 1 carbon. So down here we've got carbon I-2. And that means that up here at the top we've got H1 and H2. Okay, so we've got the orientation of the carbons and the hydrogens with respect to carbon I-1. And then in front, we can draw in what is going on over here. And so what we have is coming off the top, we have carbon I+1. And then down to the sides, right there at the hydrogens, we've got hydrogen 3 and hydrogen 4. And now what I'm saying in terms of rotation is that rotations of these atoms are permitted. Okay, so what I've drawn here is the trans conformation. All right, so in terms of this segment of the molecule, it kind of looks something like this. If you wanted to draw the Newman projection for what's going on. Now I could have a different one. Imagine that I zoomed into that part of the molecule. This trans conformation is not the only one I can have, right? I could have something that looks like this. Okay, so I've got carbon atom I+1, I-1, I-2. So my Newman projection in this case would look something like this. I would have carbon I-2 at the top. Its hydrogens would go down, so I've got coming down hydrogen 1, hydrogen 2. And then in terms of the other carbon on the other side, so one right here, it's on the same side of the molecule as carbon I-2. So I would get something that looks like that, and then I would have the hydrogens coming off in the same direction. Furthermore, this carbon atom could rotate any way around, okay? Because those bonds are flexible, that carbon atom can be anywhere with relation to the carbon atom on the other side. And so in terms of the actual polyethylene chain, you might get something that looks like this. Okay, so you could have segments of the polymer chain that look like this, after which you could have any number of different orientations of these bond vectors here with respect to each other, right? And so this is what gives the polymer flexibility. So bond rotations give the flexibility. And so you can imagine that some orientations, some conformations are preferred. In particular, this trans conformation is really good because it gets the hydrogens out of each other's way. So it creates the maximum separation between the positions of those hydrogens with respect to each other. So it's much more favored than something like this conformation here, where everybody's on the same side. This one would have a higher energy cost associated with it. Okay, so what we could do is we could plot the orientation of these things with respect to each other. So we could plot, let me be a little clearer here. We could plot the angle between these carbons that are separated from each other. So the torsion angle. Okay, and so if it was equal to 0, I'm going to say that that has the lowest energy. That torsion angle of 0 is the trans conformation, and let me draw it for you. In terms of this Newman projection, if I was to trace out this bond vector, so here's the bond vector between carbon I-2 and carbon I-1. There's also the vector between carbon I and carbon I+1. You can see that those things are in the same direction. So this trans conformation would correspond to a torsion angle of 0. Similarly, you could see that for the non-trans case that I drew here, you would have the position of the carbon I-2 atom. You would have a vector like that, the vector from that atom to the one that's next in the backbone. And you would have something like this on the other side, okay? So you'd have something that's not equal to 0. So in terms of this energy graph that I'm making here, this trans conformation will have the lowest energy associated with it, and the energy will increase symmetrically on both sides. So that out here, you get about 120 degrees. Down here you have minus 120 degrees. And what you can see is that while here you have a global minimum in the energy, out here you'll have local minima in the energy. Okay, so what I'm trying to get across here is that while the trans conformation is preferred, while we would like to have segments of the chain that look like that, there is some small chance that the polymer chain could have other angles between the carbons like that, other torsion angles, which would give rise overall to a polymer conformation that looks something like this. Okay, and again, that's going to give you the flexibility in the polymer chain. So the last part of this video, let's actually look at the conformation of the polymer. And so to do this, what we're going to end up with is a model that we call the freely jointed chain. And the way this works is for every monomer that I have in my polymer chain, when I go to place the next one in the chain, it's going to be a certain distance away, okay, such that it has a constant bond length. But in terms of the angle or the position of it, it can really be anywhere with equal probability, right? So what this means is, let's consider that I have a polymer chain. So suppose I have a polymer chain with a total of little n plus 1 monomers. And they're going to have a constant bond length, but any angle. And we saw why that is, right? They can have any angle because of the bond rotation, which imparts flexibility onto the polymer chain. So let's label the monomers and start to draw them. So for example, I'm just going to make this up. But let's say I start somewhere with the beginning of the chain, A0, and then I'm going to move a certain bond length away, and I can put my next monomer anywhere I want. So let's put my next monomer over here. That's A1. And then I'll put my next monomer over here, A2. And I can put my next monomer, again, I'm just doing this kind of randomly. There's no rhyme or reason to how I'm doing this. Okay, and now between each of these monomers, there's going to be a bond vector. So there's going to be a vector between monomers 0 and 1. We'll call this R1. There's going to be a vector that has the same magnitude between monomers 2 and 3. So this we would call R2. Same thing here, we would have R3. Let me draw in the remaining ones. I've got over here R4. R5. And then the polymer chain's huge, right? I mean, it's got thousands and thousands of monomers. And so it goes off somewhere. I don't know what it does. It does its thing over here. And at the end of the day, it ends up over at a position, the last monomer of the chain, A sub n, ends up way over there, okay? Because of all this random flexibility and stuff. The one thing that we could use to figure out the size of the polymer chain is, what is the distance between the start of the chain and the end of the chain, right? That seems reasonable. So this vector between the end of the chain and the start of the chain will give us some information, we presume, about the size of the polymer chain. So this thing, let's get some terminology here before we do anything. R sub n is going to be very important. This is one of the most important things we're going to use in our description of polymers. We're going to call this the end-to-end vector. And again, it's very important. And let's see what else. We will call R sub I the bond vector for monomer I. And what it is it's a difference in the positions between the two monomers. So R sub I we could define as the position of monomer I minus the position of monomer I minus 1. Okay, so that's how we'll define it. Other things, the magnitude, so the magnitude of R sub I is equal to the bond length L always. Okay, so that's always true. And then finally, if we wanted to calculate R sub n, all we have to do is add up all of the individual bond vectors for the polymer chain. Okay, so this will be equal to R sub 1 plus R sub 2 plus R sub 3 plus R sub n. Right? So in other words, the end-to-end vector is going to be the summation of all of the bond vectors. Finally, okay, so let's call this is our first kind of condition for this. Our second one is how we're going to define the end-to-end vector. So we'll sum up all of the bond vectors. And the final thing is that theta ij is the vector, is the angle between vector r sub I and r sub j. So in other words, if you look at any two monomers in the polymer chain, there's going to be a bond vector associated with each of those monomers. And so theta ij will be the angle between two vectors that are separated along the polymer chain, right? Between monomer j over here and monomer I over here. So for example, if I had something that looked like this, if I had some adjacent monomers, okay, so for example, then if this is monomer A sub I, then this would be bond vector R sub I. If this was monomer A sub j, then this would be bond vector R sub j. And that means that this vector, this angle here, theta ij, would be the angle between them. Right? Or maybe it's clearer if I do it this way. If I was to translate this vector over here, it would look something like this. And so this would give you theta ij. Okay, so those are all kinds of the basic definitions. And one thing that I'm saying is by using the term freely jointed chain, you'll also see me write this a lot. You'll see me write freely jointed chain. Then what I'm saying is that the chain is freely jointed in the sense that if I have three monomers like this, then again, here's going to be one bond vector. Then the third monomer that I'm showing over here, that monomer could be anywhere. And so when I'm looking at coming up with a position for that monomer, it could be anywhere along this kind of path like this. In other words, if I translate this vector up, so if I move R sub I over here, then this angle theta ij can be anything. Okay? And the only values that it could have then would be theta ij has to be between 0 and pi radians, right? In other words, between 0 and 180 degrees. If it was 0, then you would get your next monomer over here. If it was 180 degrees, then your next monomer would be over there, right? And you'll notice that that means that the two monomers would overlap with each other. That's something that can happen in the freely jointed chain. You can allow the monomers to occupy the same space. Okay, that's a point that we'll touch on later, but just for now, realize that what we're saying for a freely jointed polymer chain is that each bond vector can really take any angle like this. All right, so the polymers are just big floppy molecules. Okay, so what we want to look at then is what is the size of this polymer chain? We're going to get the size of the polymer chain in terms of this end-to-end vector. But we can't just do it for one polymer, right? I mean, one polymer will have a certain arrangement of the monomers, but that's only one polymer chain, and that's only one specific condition, what we really need to do is average over a large number of polymer chains. And so we're going to look at this quantity. These brackets denote an average, and we call this the ensemble average because we're going to average over a large number of molecules, okay, so that we can get something that's statistically relevant. Now the first thing, and again, this means average over all polymers. Okay, so if you have a beaker with 1 weight percent polymer in there, you're going to average over the billions of polymer chains that are in that little beaker to get an idea of what the representative size is. So the first thing is I'm going to claim that this is going to be equal to 0. Okay, so that's problematic, and this is why we're going to use the HoloLens. Why on earth would that be equal to 0? Well, let's look at it a couple different ways. One way is if we look up here, this thing looks like a random walk. Oops. So what I'm interested in is how far away is my chain end from where I started. So we can make an analogy to the random walk, and we could plot the probability, and we know that if we take a large number of steps, then that's equivalent to having a large molecular weight, right? Because each of these bonds between the monomers over here, each of those is kind of like a step. So if we have a large number of steps, and we have a large number of monomers in our polymer chain. And so if we're going to look at our position, then we know that this is going to look kind of sort of like a Gaussian distribution. And so our most likely position is going to be the peak of that, which is at 0. Okay, so that's one way that we can do it. The next way that we could look at the fact that the bond vector on average is equal to 0 is we can look at what the polymer chain is. So we can look at all the bond vectors and let's connect them to the same origin. So for example, let's take the first bond vector, that one, and put that at the origin, and then move the second one, which is this one, move that to the origin. Okay, and remember, any direction is possible with these bond vectors. So the first bond vector might look something like this. So this would be R1. And then we connect R2 to it. So you'll notice that R2, in this case, looks like this horizontal line. So we'll go down here, and here is R2. Now let's look at R3. R3 is right here. Okay, so we can move that to the origin. So R3 kind of sort of looks like this. Where's R4? R4 is down, so R4 looks like that. Right, that one right there. So if we move that over here, R4 looks like that. And you can see that the direction of R1 and R4 kind of cancel each other out. Okay, so what we're going to do is add more and more monomers to our polymer chain, and we're going to look at more and more bond vectors. And since they can have any angle, then we anticipate that on average, they're going to point in all directions, right? Because nothing's really preferred, everything's equally probable. And so if that's the case, then you can see that the summation of those should be equal to 0 because it's completely isotropic. Okay, so that's another way of getting at that. So the bond vectors are isotropic, which means that the summation of the bond vectors equals 0 because they point in all different directions. So that's another way of getting that. Okay. So what can we do? Well, if we're getting 0 for this, because they're all pointing in different directions. And why don't we just look at the sum of their magnitudes and see what that gives us? So instead, let's look at this thing. What is the average value of Rn squared? Remember, we're talking about vectors, so that is the same thing as Rn dotted with Rn. All right? So in other words, what we're looking at, to use our language, is that these things, these brackets, are telling us that we're looking at the average, the ensemble average, or the mean. That little 2 there tells us that it's squared. So this is going to be called the mean squared into end distance. And we can calculate it. So for example, let's just plug in and do that. So R sub n, we know how to calculate that, right? This is just going to be the summation over I of R sub I dotted with summation of J R sub J. And we have to use different indices I and J because we have to separate the two out, right? These things are independent of each other. And so that's our definition for the mean squared end-to-end distance. So what we can do is combine these. This is going to be the same thing as the summation of I, summation of J, of R sub I dotted with R sub J. Why? Because these summations are independent of each other. So what we've done is we've combined them. Okay, so this is R sub n squared. So that's pretty important. Now we know that the magnitudes of each of these is just the bond length. And we know that if we have two vectors, if you think back to multivariable calculus or to your physics classes, that if you have two vectors A and B, their dot product is the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between them, right? So that means that our mean squared end-to-end distance is going to be L squared, because the vectors have the same magnitude, summation over I, summation over J, of the average of the cosine between any two vectors, right? Any two bond vectors. Now we expect this to be 0, so we expect the average of the cosine of theta ij to be 0 if I is not equal to j, right? Why is that? Because they're pointed in all different directions. So on average, there's going to be a bond vector pointing this way, and the sum of all of the other ones that are pointing in all the other directions will cancel out and we'll get 0. And so we also expect that cosine of theta ii will be equal to 1 because the bond vector is always going to be parallel to itself. So this is what we expect. We could prove it if you wanted. So if you want to prove that, what is the average of the cosine between any two vectors if I is not equal to j, you can calculate that, right? Mean value theorem, it's 1 over the period times the integral over that period of cosine theta ij d theta ij. And so what you're going to get is 1 over pi, that doesn't matter, sine of theta from 0 to pi equals 0. Unless if j is equal to I, then the cosine of theta ii would be the cosine of 0, and that would give you 1. So this simplifies our expression up here for the mean squared end-to-end distance. So this term in the brackets, this cosine theta ij, is going to be 0 unless j is equal to I. So that's going to get rid of one of our summations, and this will look a little simpler. What we're going to end up with is the mean squared distance for the polymer chain, the mean squared end-to-end distance, will be L squared summation over I of 1. And that goes from I equals 1 to n. So there will be n of those, and we get nl squared. This is very, 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 very important. Okay, so if that didn't make sense to you how we got this, go back and think very carefully, go back to the video and listen very closely to what's going on. Basically what we're saying is that if you have two vectors where I is equal to j, then theta between them is equal to 0, always, 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 always. And so cosine of theta is equal to 1. If I is not equal to j, then we have one vector that looks like this, and we have a second vector that could have any direction, right? It could have any orientation. And so in that case, the average of it, when everything is averaged out, we get that the average value of that will be 0, because on average the vectors will be perpendicular to each other. And that's how we get this expression here, which again is super important. So let's look at what that means. Let's go back to our polyethylene example. Okay, so again, we've got polyethylene. The molar mass is 150,000 grams per mole, and the mass of the monomer, M0, is 28 grams per mole. And we calculated earlier that the maximum length of the molecule is 684 nanometers. And I said that if you were to go into the lab and do an AFM measurement or something to see how big those are, you would find that the polymers are nowhere near that, right? They're smaller than 1/10 of that. This is at least an order of magnitude off. Now, if we wanted to calculate its end-to-end distance, mean squared end-to-end distance, then we can substitute this in. We've got L squared, so 154 nanometers squared, multiplied by N. N is just the molar mass of the polymer, divided by the molar mass of the monomer. This would be 127 nanometers squared. Okay, so it's maybe a little bit hard to compare these two. So we could calculate what's called the root mean squared. And that would be r squared to the 1/2 square root of 127 nanometers. So this would be about 11 nanometers. So compare these, right? I mean, compare, you've got the maximum length of this polyethylene chain is 684 nanometers, but the actual size, because it has flexibility, because the bonds can rotate, the actual size of this polymer chain is much smaller, right? Not anywhere close to that. Okay, so the polymer chains are actually much smaller than what you would think is it if you fully pulled out the size of that. And so how did we do this? Again, we got this with a random walk. In this case, instead of taking a step in the random direction, we created a bond between monomers that could be oriented in any direction. And so that's the connection between the random walk and the ideal polymer chain model. I should say the freely jointed ideal polymer chain model, is that the bond vectors are oriented with any direction with equal probability, and the result of that is that we get this very simple expression for the size of the polymer chain, and that gives us a size that's much closer to what we would expect to see. And so the assumptions in doing this, which is really important, The assumption in doing this is that N is very large. So everything that we've done breaks down if you have a short molecule. So this breaks down for short oligomers. Okay, so if you've got like 10 monomers or something like that, this approach that we took is not going to work. The other assumption is that any bond angle is possible. Okay, that's what we mean by freely jointed. Freely jointed, this thing is super flexible and any angle is possible. Which that's implying that there is no correlations between the direction of any two bonds. So if we want to say that another way, if we're looking at two monomers, I and J, that are really far away from each other, so their monomer index is really different. So the 500th monomer way over here versus the first monomer in the chain, as that distance goes to infinity, what we're figuring is that the average value of the angle between those bond vectors is equal to 0. So that's kind of assuming a lot, right? Because really, if you think about polymer chains, let's look at something like polyethylene versus something like polystyrene. Okay, so we've got polyethylene over here and polystyrene over here. Now, you could go through the same sort of analysis, but the issue is you've got this really bulky side group in the case of polystyrene, which could cause local correlation. So this could cause local correlations in bond vector direction. And if we were just guessing by looking at the structure of the polymer, you might expect that the correlations for polystyrene would be greater than the correlations for polyethylene, because polyethylene doesn't have that bulky side group to restrict how much these bond vectors can, restrict how much these monomers can rotate with respect to each other, which will affect the direction of the bond vectors with respect to each other. So you would expect more local correlations for polystyrene than for polyethylene. So there would be fewer correlations locally. And so this is going to impact our model for the polymer chains just a little bit. And so what we had in general is we can define this correlation as a summation j equals 1 to n of the cosine of theta ij. And so this is a measure of local correlations for the bond vectors. We could also define C sub n as 1 over n times the summation from I equals 1 to n of Ci prime. So in other words, what we could do is we could look at these local correlations and look how big they are and calculate what that effect would be for the size of the polymer chain. So for example, if you trace through everything that we've just done, then these definitions would lead to an expression that looks like this. We would have the mean squared end-to-end distance would be equal to L squared times the summation I equals 1 to n of Ci prime divided by n, which would give us Cn and L squared. In other words, we're not going to assume that we get this summation where everything is 1, like we did right here. Instead, what we're going to look at is the effect of having some kind of correlation where this value is not equal to 1. And by summing them all up, what we end up with is a term up front that looks like that. Or maybe I should just circle the C sub n, right? So this describes local correlations for the bond angles. So it's kind of sort of like a fudge factor. And so if we have a lot of monomers, like much, much bigger than 1, then what we end up with is R squared is equal to C infinity times NL squared. So this is what we tend to use. It's one of the formulas that we tend to use. So let's compare this, okay? So what we've done with polyethylene so far is we looked at R max, which was 684 nanometers. And then what did we do? We went and calculated what its root mean squared end-to-end distance would be if it was a freely jointed chain with no correlations in the bond angles. In other words, the bond angles are completely unrestricted. If we start to look at the effects of chemistry now, we would see that R squared to the 1/2, and I encourage you to plug in and try this, is going to be equal to C infinity times NL squared. Should take the square root of this, right? And we can look up in a textbook what C infinity for polyethylene is. And what we end up with is a size of 31 nanometers. Okay? So to summarize this, if you were to grab onto the polyethylene chain and pull it out as far as you could, you would get a length of 684 nanometers. When we put that on a surface and do AFM to try to figure out how big it is, we find out that that's not the case. We can estimate what its size would be if we assume that there's absolutely no correlations between the angles between any two bond vectors. And then we can start to incorporate some local correlations that we know from the chemistry of the molecule. Generally, we figure these numbers out, these values C infinity, we figure these out by measurements. We call these characteristic ratios. We call them C infinity. And so for polyethylene, that happens to be 7.4. And so because of those local correlations between the orientations of the bonds, we get a slightly bigger polymer chain. So actually, if we were to go do the experiment using AFM or something like that, the size of our polymer chain would be closer to 31 nanometers. Finally, we could compare that to something like polystyrene. So if polystyrene had the exact same bond lengths and degree of polymerization, we could calculate how much bigger polystyrene would be, and we could look up C infinity for polystyrene. And we would find that value is about 9.5. And so this means for polystyrene, the root mean squared end-to-end distance would be, again, C infinity and L squared, and we have to take the square root of that. And we would get 36 nanometers. And so what this means is if you have a polymer like polystyrene, where you have this large group that can start to cause local correlations in the orientations of the bond vectors, then that leads to a larger value of the characteristic ratio, which in turn leads to a larger value for its root mean squared end-to-end distance. In other words, that bulky side group leads to correlations in the bond vectors, which leads to a larger polymer chain. So compare that. Freely jointed chain, 11 nanometers, no restrictions on bond angles. Something like polyethylene with a small amount of restrictions on the bond angles, we get a larger radius of gyration of 31 nanometers. And if we look at something like polystyrene, where again, we're increasing the local correlations, because we have more restrictions on those bond angles, we get an even bigger polymer chain. But the last thing I want you to notice is that for all of these polymers, this mean squared end-to-end distance looks like something that has to do with the chemistry times NL squared. And so when we're coming up with models to describe the behavior of polymers and the materials that they make up, what we'd like to do is instead look at something that we call an equivalent freely joined chain. Okay, so when we do this, we take advantage of the first thing that we notice about polymer chains is that they seem to exhibit universal behaviors. They exhibit universality. In their size. Okay, so all of them have a size that looks like the number of monomers multiplied by the bond length squared, except that there's some little thing that goes in front, which has to do with their chemistry. And so what we do is we take a bunch of different polymers. So for example, if we have polyethylene, or if we have polystyrene, or something crazy like maybe polyacrylic acid, these all have different characteristic ratios. But what we would like to do though is translate them so that all polymer chains kind of look like this. So we're turning them into an equivalent freely joined chain. So what I mean by that is, first of all, we take the polymer and we stretch it out. Let me do an example with polyethylene. So we have polyethylene like this. And we stretch it all the way out and calculate R max. So we stretch it out like this. And so on, right? And so this polymer chain is going to have a total length R max is equal to NL cosine of theta over 2. Okay, so this is the actual chain. This is what I would call the real chain. And what I would like to do is replace it with an equivalent chain where I have capital N equivalent monomers, and each of those equivalent monomers will have a bond length of B. So what I want is R max for the real chain equals R max for the equivalent chain. And you can see for this equivalent chain that R max, because I've stretched it out like this, is just going to be B times capital N. So little n is the number of actual monomers that you have. Capital N is the number of equivalent monomers that you have. And in other words, we group some of them together. Okay, so we kind of rescale the problem a little bit. So what we have in this case is that NL cosine of theta over 2 should equal to B times capital N. The next thing that we need is we need to figure out, okay, so this is setting R max equal to each other. The next thing that we want is we want to set their mean squared end-to-end distances to be the same. So we get b squared n. That's going to be the mean squared end-to-end distance for the equivalent freely jointed chain. Should be equal to c infinity and L squared. So we set R squared to be equal. Okay, so doing this, we can map the real polymer to a fully freely jointed chain. All right, so for example, we could use these two expressions to relate the parameters, to relate little n to capital N and the bond length to the bond length of the equivalent chain. Okay, so for example, I'll just give you the results. Capital N would be R max squared over B squared N, which would be R max squared C infinity N L squared. Okay, so if we know the maximum length of our polymer chain and we know C infinity, then we can calculate what N is. Okay, so we can calculate the number of equivalent monomers. We call those the number of Kuhn monomers, after the scientists in the early 20th century who did a lot of work on these models. The other thing that we can do is we can calculate B, that equivalent bond length, as C infinity N L squared divided by B times N. This would be the mean squared end-to-end distance divided by R max. And so what we use this for is to calculate the equivalent bond length of the freely jointed chain. So by doing that, we're calculating how long the effective bond vector has to be so that it's not correlated with any of the other bond vectors in the polymer chain. We call this the Kuhn length, or the statistical segment length. Okay, and that's how we map one thing onto the others. So that is the heart of this video. In the next one, we're going to talk about other ways to calculate the size of a polymer chain. And what we're going to find is that for any polymer, we can always calculate an equivalent freely jointed chain for it. And one thing that we might do if we wanted to figure out the size of this molecule is we could find its center of mass. And then once we do that, we could calculate on average how far away is everybody from the center of mass of the molecule. So on average, how far is a certain monomer from the center of mass of the molecule? Oops. So we call this distance, come on. 1 second. Okay, so something like that. We call this distance RG, or the radius of gyration. Okay, and this is something that we're going to visualize with the Microsoft HoloLens. But what we'll find is that its value, RG, is that Kuhn length times the square root of n divided by 6. And we'll see where that comes from in the next video. But the highlights here, the most important thing is that the fully extended length of a polymer chain is going to be much, much greater than the actual length because there's some flexibility in the molecule. Okay, so if we assume that the molecule has infinite flexibility, then we get the freely jointed chain, and we can calculate the size of the freely jointed chain very easily based on the number of monomers that are in there and how far they are apart from each other, what the bond length is. But real polymers have chemistry. They have things like pendant groups, stiffness in the backbone, different things like that, that lead to correlation. So the chain isn't truly 100% flexible. And what these local correlations do is they lead to corrections to the values that we would get for the size of the polymer chain from the freely jointed chain model. And those are captured by the characteristic ratio. And so you saw a comparison between those characteristic ratios for two polymers and what it does for the actual size of the molecule. And then the very last thing that's important from this video is that regardless of the chemistry that we see in our polymer chains, we can always construct an equivalent chain that is freely jointed that has all of the properties that we know, but just has a rescaled value of the bond length and a rescaled value of the number of monomers. And by setting these values equal to each other, so for example, by setting the maximum chain length R max between the two models equal to each other, and by setting the mean squared end-to-end distance between the two models equal to each other, we can calculate what the effective number of monomers in a freely jointed chain is, and what the effective bond length is in a freely jointed chain for that particular polymer. And so we use this all of the time. Finally, there are other ways to calculate the effective size of the polymer, not just using the distance between the chain ends, which I'm kind of showing here, right? That's R sub n. We can also do it from the center of mass of the molecule, and we get an expression for what we call the radius of gyration. Okay, and these are concepts that are central to polymer physics, polymer physical chemistry, and things that we have to use to really figure out what the size of our molecule is and how that size affects the properties.